and I'm Takatomi Kubo, an associate professor of NICE Japan. In fact, this is the first time for me to join SE Motion and ICSI. So actually, I'm not familiar with conferences in software engineering, but I'm willing to discuss our research topic with you. And I strongly hope that you will have any interest in my research topics. Okay. So first, let me briefly introduce myself. I graduated from the Faculty of Medicine, Osaka University, and I got my medical license there. And after that, I got my PhD degree in engineering from NICE Japan. So my main background is medicine and informatics. By the way, this image shows a panoramic view of NICE. And with respect to work history, so I used to work as a medical doctor, as a neurologist for almost 6 years. And after that, I have been working for my current laboratory for 8 years. Okay, so next, let me introduce my research interests. So from the experience as a medical doctor, I have considered how to treat, alleviate, or prevent cognitive disorders, including consciousness disorders, aphasia, and other disorders of higher cognitive functions. Here, aphasia is a language disorder that makes a patient unable to speak, write, or understand speech or written language. Based on my experience and knowledge, I come to have interest in the ability of program comprehension as a unique cognitive function. In addition to medicine and informatics, I have experience of neuroscience research project as well. And with such background, I have launched an fMRI study on program comprehension recently. In this work, advanced signal processing and machine learning techniques are used from my background. Yeah. Actually, the title of today's talk is Neural Information Processing in Experts Program Comprehension. And I know ICSI has another workshop called ICPC, but I hope my talk is not out of place. Yeah. So I would like to mention 2 points here. So first, the framework I will introduce would be applicable not only to program comprehension, but also to emotional aspects. Okay. Next, I would like to add a brief introduction of our studies related to emotion for your reference. So this is not scheduled in my talk, but I added. So, but unfortunately, it is not related to software engineering. So I have no project in the intersection of software engineering and emotion. But anyway, let me introduce my study. Apart from today's topic, I'm conducting several studies which use heart rate variability to evaluate the state of autonomic nervous system and stimuli to the autonomic nervous system like stress, emotional change, etc. The left figure shows the autonomic nerves that control rhythm of the heartbeats. The right top figure shows the waveform of electrocardiography or ECG for short. In this figure, R wave, the peaks in this figure are known as the electrical activity that corresponds to the contraction of the ventricular. The interval between a successive pair of R waves is called RRI. This RRI is not constant over time. The right bottom figure shows spontaneous fluctuation in the series of RRI. In this figure, the vertical axis shows the value of RRI, and it is known that this fluctuation is related to the state of the autonomic nervous system. Then several metrics have been proposed to evaluate this variability of heart rate. My collaborators, Dr. Yamakawa and Dr. Fujiwara, have developed the HRV monitoring system to record RRI, HRV, and event information. This system consists of a device shown in the left figure, smartphone and mobile app. This device is smaller and lighter than commercially available usual products. Its weight is just approximately 40 grams. Also, it can keep on running for almost 2 days. So we are now distributing multiple systems to collect HRV data from tens of subjects simultaneously now. In this app, we implemented an annotation tool to collect event information with logged HRV data. So thanks to this function, we can easily collect a set of HRV data and annotation easily. With this system, we have been doing several research projects. For example, we have collected HRV data from the subject who had mild symptoms of heat stroke. Also, as is shown here, we have conducted multiple experiments. So we have investigated emotional change by music, driver's mental state, and dog's emotional states with HRV analysis. If you have any interest in our system or our studies, please feel free to contact me. Okay. Now, I would like to start today's main topic. But before that, I would like to define neural information processing in this talk. So some of you may know a conference called Neural Information Processing Systems, or NeurIPS for short. For your reference, I cited remarks from its website. This is not the definition, but I thought this could be a good reference. So it says, neural information processing is a field which benefits from a combined view of biological, physical, mathematical, and computational sciences. So we can say the target is computational principle in information processing of the neural system, not the neural system itself as a concrete body or hardware, unlike conventional biology. And my direction is actually similar to the NeurIPS. To consider the computational principle and its application, I would like to cover computational aspects of the neural system. So I define the neural information processing as information processing executed in the neural system or system that imitate or model biological neural system. Okay, and I would like to introduce a study submitted to bioRxiv, and the current arithmetic score of our preprint is 205 points. So it means it is ranked in top 1% paper. So yeah, now our paper are receiving very strong attention from the research communities. So in this study, we investigated how our brain works during program comprehension with a neuroscientific approach. This study is a collaborative research work with CNET. And Yoshiharu Ikutani conducted the experiment and analyzed data with me. Okay, I think needless to say, programming expertise attracts attention of the society. And nowadays, education is provided not only to adults, but also to young children. Regardless of such situation, scientific evidence is not yet well established for efficient education process. It is because the programming expertise is relatively new ability, and it is based on a very complex cognitive processes. Of course, there are many related research works. And some researchers have revealed that expert programmers exhibit remarkable differences in behavioral performances and selective attentions. A pioneering study by Sackman et al. Reported remarkable variation in productivity between programmers, even with similar time lengths of their experiences. They reported very large differences in debugging speed, coding speed, and other metrics. In addition, some researchers have been investigating psychological and behavioral characteristics of expert programmers. For example, Van et al. Identified specific eye movement patterns of expert programmers during program comprehension. Also, these results show the evidence of the behavioral superiority of expert programmers. The neural basis of their expertise still remain unclear. There are several research works that analyze brain activity during program comprehension. In these studies, researchers used electroencephalography, functional near-infrared spectroscopy, and functional MRI to measure brain activity. I think some of you may know usual MRI that are used for medical examination. It is used to measure the structure of the body, including the brain. On the other hand, functional MRI is used to measure the function of the brain. As the principle, fMRI measures the blood oxygenation level. And active brain region requires more oxygen during task than resting state. The more oxygen is delivered by an increase of brain blood flow. fMRI measures the change of the signals that reflects the brain activity. We can find several works that analyze brain activity during program comprehension using fMRI. For example, Zygmunt et al. Investigated it by comparing the brain activity during output estimation and syntax error search. As a result, they found that language-related brain regions are more activated in program output estimation than syntax error search. But there are several issues in this study. First, how to interpret the comparison between tasks like these are not easy. With this approach, we cannot mention the functionality of source code. Second, they did not analyze the relationship between the brain activity and the level of expertise. So in our study, we aim to identify the neural basis of program expertise that actually contribute to experts' outstanding performances. To achieve this objective, we try to associate individual programming expertise with the cortical representation of source code measured by fMRI and decoding approach. Here, let me explain decoding. Let's assume we conducted an experiment shown here. We have a set of stimuli like these images, and we presented them to a subject as visual stimuli. We collected the datasets that contain brain activity data and corresponding label indicating a discrete class of stimuli. By using pairs of label and corresponding brain activity, machine learning model can be trained as a classification problem. For example, support vector machines are often used in the neuroscience. With this trained model, we can predict what types of stimuli were presented to the subject. This is the decoding approach. Then let's substitute source code for the images. And here, we assume that we can define the categories of such source codes. After collecting brain activity corresponding to every category, we can train a machine learning model again. If we can decode the category of source code from the brain activity, it means that information of source codes are represented in the brain. Before our study, there was no research work that used decoding approach for category of source codes. Also, in this study, we used searchlight decoding. This is a kind of data-driven exhaustive search for the location where brain decoding shows significant accuracy using a spatially moving window. Briefly speaking, without defining target location, we computed decoding accuracy for all possible locations. Okay, let me move on to the experiment. In the beginning of this study, we determined 3 recruiting criteria to cover a wide range of programming expertise. We used programmers' rank in a competitive programming contest as an indicator of programming expertise. Experts and middles are top 20% and top 21% to top 50% rankers, respectively, in a contest of at-coder. While the novice criterion is non-expert with less experience. This table shows statistical characteristic for each group. But anyway, successfully we recruited the subject as we intended. And we made a dataset that contains 30 programmers in total. In the experiment, we used 72 types of Java code snippets collected from EyesOnline Judge dataset. Each snippet was assigned 1 category level and 1 subcategory level. For example, a snippet implementing primality test function was included in math category, and as the subcategory level, the algorithm name itself is given. For all subjects, we instructed to perform program categorization tasks inside the fMRI scanner. The task consisted of 3 phases. The first one is the baseline, where subjects gazed at fixation cross sign. The second phase is source code reading to categorize given code snippet into one of the 4 functional categories. The last one is response phase. In this phase, subjects respond their answer using buttons. All subjects performed 216 times of this program categorization task. During the task, the brain activities were recorded with fMRI. So every subject took training session before MRI measurements to learn what to do in the experiment. After that, they participated in main fMRI experiment. Also, all subjects performed subcategory classification experiments to assess their performance of subcategory categorization. In this talk, I will focus on mainly results in fMRI experiment. With this experimental procedure, we obtained brain activity data from 30 subjects while they categorize the given Java code snippets. We used this brain activity dataset to decode functional category of source code and assessed the relationship between expertise level and brain representation pattern. Let me remind you that our working hypothesis is whether higher programming expertise relates to multivoxel pattern in the brain. I would like to move on to the results of behavior analysis first. These graphs show the relationship between individual behavioral performances and at-coda rate. The horizontal axis indicates at-coda rate and the vertical axis the behavioral performance. As you can see, we observed clear significant correlations between them. This indicates that our experimental design successfully captures individual programming expertise. Importantly, these results enable us to expect programming expertise can be reflected in their brain activity through this program categorization task. Next, we examined which brain regions have significant decoding accuracy of source code. We calculated decoding accuracy for all subjects. Successively, we calculated the mean and variance of the accuracies across subjects. In this result, we used t-test to assess significance of decoding accuracies of every voxel. And only significant regions are shown here, but we used multiple test collection to collect multiple tests. Please note that fMRI data usually has tens of thousands of voxels or more. Therefore, multiple test collection is crucially important. Through this analysis, we can say early visual cortex, posterior temporal lobe, parietal lobe, and prefrontal cortex have sufficient information for the decoding as the representation of source code category. Next, we investigated which brain regions showed the significant correlation between decoding accuracy and individual performance. In this analysis, we use t-test again, and the regions that showed significant correlations are shown in red or yellow. We found that significant correlations are observed in posterior temporal lobe, a part of parietal lobe, and prefrontal cortex. Interestingly, significant correlation was not observed in the early visual cortex in this result, although it had significant decoding accuracy of source code categories in the previous result. Finally, we identify the regions that have sufficient information of source code category and significant correlation. It means we visualized the intersection of previous two results in red color in this figure. As a result, we conclude that cortical representations of the 7 brain regions are correlated with expert superior performance in this experiment. I will explain how to interpret this result in the discussion. Okay. So let me explain the potential role of these regions in programming expertise. With respect to the left IFG and MTG, Many fMRI studies have indicated that these regions are related to semantic knowledge retrieval in the processing of natural languages. Our results suggest that higher programming expertise might be related to natural language processing, in particular, semantic knowledge retrieval. For left IPL and SMG, two different roles have been mentioned in the literature. One argued that these regions are associated with visual word reading, and the other say episodic memory retrieval is related to this region. Our results may imply that expert programmers might have different reading strategy or domain-specific memory than novices. One of the novel findings in this study was the potential involvement of the right hemisphere. The previous fMRI studies on programmers have not argued the involvement of right hemisphere, but functional role of right IFG and MFG are unclear. Here, just as one possible interpretation, stimulus-driven attention control is related to these regions. Several expertise studies demonstrate that chess and abacus experts show the involvement of these regions. Thus, our results may imply that programming expertise might have similar developmental process as other expertise like chess and abacus. Okay, this is a summary of our fMRI study. Functional categories of source code can be decoded from programmers' brain activity. Decoding accuracy of some brain regions were correlated with behavioral performance of experts. Our results revealed that tight association between programming expertise and programmers' cortical representation. And this QR code provides a link to our preprint. So far, I have discussed how human programmers understand source code. From now, I would like to mention other ongoing studies and our future direction. As the next step, we have interests not only in the human brain, but also in machine intelligence. So, previous research works has developed a model that can process the set of source code, but most of them are using existing methods in the machine learning field. We are developing machine learning models by introducing prior knowledge about the codes into the models. Here, how to treat syntax may be a very important point in this study. To consider that we are studying about how human subjects can comprehend source code. Also, we are considering to compare the human brain activity with some models. Recently, there are some research works that compare the human brain activity and parameters or values in the hidden layers of the model. Even in the brain activity of program comprehension, we may derive some findings about the neural information processing in the brain. This is my expectation. In addition, we have conducted eye tracking experiments during program comprehension. We will compare the attention of human subjects with that of machine learning models. Recent machine learning model has a module that is called attention. This attention mechanism can select important information in the input feature. We will compare human gaze behavior and attention in machine learning model. Through this comparison, we would like to get the feedback information from human to model or from model to human. Also, by finding a commonality between them, we will derive the finding about the human attention during program comprehension. And through that, we would like to explain how human subjects recognize source code. Okay, this is a summary of today's talk. In the fMRI study, functional category of source code can be decoded from programmer's brain. Multiple brain regions are identified as the neural correlates of programming expertise. These regions widely distributed in the frontal, parietal, and temporal cortices. It may mean program comprehension needs rather diverse cognitive function. As the future direction, I introduce several topics, and we will analyze gaze behavior of programmers in the near future, and modeling approach can be complementary to the classical analysis, especially to elucidate the neural mechanism. Okay, so finally, I would like to thank all of my collaborators and grants, especially Yoshi, Takeshi, and Kiyoka. And also, I would like to thank the organizers again for this valuable opportunity. That's all for my today's talk. Thank you for your attention.